Okay, so the recording has started. Good morning. My name is Sandy Baresi Shagota. You should remember me from yesterday for Big Data class. So let's talk today. So today we have the second topic, and we're going to discuss data processing and analytics in big data. So techniques for data mining, some algorithms that you should know even if you aren't a big data engineer directly, if you are in different areas, and that's what we're going to essentially discuss today. Okay, so let's start with introduction to something I talked yesterday about. I mentioned the term batch processing versus stream processing, so let's go a bit more in depth about that. So batch processing, when we're talking about it, it refers to processing large volumes of data in a certain chunk of data. So instead of processing data point by point, we're going to process it. We're going to process 100 points at a time or 200 points at a time, whatever we decide. This is usually scheduled to be done, regularly. So hourly, daily, and weekly, and that's basically what helps us decide the size of a chunk that we're going to be using for processing. If you know that we collect 10,000 data points in a day, then we are going to maybe process 1,000 each hour, just so we have some extra space to do that. The problem with batch processing is that you have a high latency, because there is so that it introduces a delay. So if I am doing batch processing once a month, the data that's been collected on the first of the month is going to be processed in 30 days time. So that's a lot of latency that can be introduced with batch processing. Is not good if you're trying to do some real-time analysis. What do? We do it usually, if you remember, I mentioned ETL, extract, transform, load tasks a lot, where we are grabbing a certain amount of unstructured data and then extracting the information we want from it, transforming that information into a structured form, and then loading it into a certain structure, like a table within a database or something like that, where we want to store that. The second example is data aggregation tasks. Data aggregation simply refers to grabbing different types of data and sorting them in different classes. So, for example, if you have a lot of measurements from different sources, you have maybe a measurement from your if you have a smart home, maybe you have temperature measurements, maybe you have temperature, humidity measurements, whether a person was present in the room or not. You can, data aggregation is just collecting these different sources and setting them appropriately. Why do we want to do batch processing? Well, it's efficient on very large data sets. Why? Because you can do them all at once. And that's, if you remember, when I mentioned elastic computing when we're talking about, in data storage and management class, right? When we're talking about like hiring computer resources, if you're hiring them elastically and you're hiring, different processing powers at different times, that's something that's going to be useful to you, because you can just hire more CPU power when you're doing the processing, and then discard that, pay less for the rest of the month. So that's somewhere where batch processing is useful. Dependent to that is stream processing, where you have real time data, and as soon as you receive a certain data point, whether it's an image, a vector of data, or whatever, you are going to process it immediately. This compared to batch processing, you have a low latency because you're processing data as it comes. There is some latency in data processing, where latency is described, from the point where you received the data to the point that you have processed data. Right, there is some compute time in there that you're going to need to use, but there is different, but it's much less than what you would have with batch processing. This is necessary in a lot of cases. For example, fraud detection is an example here. You don't want to detect, fraud 2 months later when the person is already gone with the money. You want to detect it immediately. You want to process sensor data immediately. If you're having something like smart home, I use that as an example for aggregation. You might batch process some data, historical data to see, for heating, whether it was necessary or not, etc. But for stuff like I wanted to turn the light on whenever I detect someone's presence, or when the phone connects to Bluetooth, I want to process it. I want to, I don't know, open the garage door or something like that. You want to obviously process that immediately. You don't want to open the garage door 2 months later. So that's something where you would use stream processing. You would process every bit of data as it arrives. And obviously it gives it requires real-time insights and allows you to automatically respond to stuff that is happening, right? With batch processing, it's useful for historical analysis. If you want to look what was happening, how we are going to adjust our strategy going forward. While with this, with stream processing, you process the data immediately and you immediately can respond to that. Obviously, what are the challenges here? You need to handle data, complex state management, etc. This all essentially boils down. Let me simplify it for you. You require more compute power. You need more powerful CPU. Now, don't, again, I said that before, I'm going to repeat it. We're talking about big data here. And when we are talking about big data, we are talking about processing, 1 megabyte of data second, because a lot of students, again, from my experience, have a mistaken perception of what big data is, and that's what I'm trying to impress upon you. It's not a problem to process, real-time data when you have a single data source, a single temperature probe, and you're trying to determine whether it's whether the temperature is appropriate or not, whether you want to turn AC or not, and that's what most people encounter. And even in the example, some of the examples I'm giving you, they're simplified to help you understand them. But then a lot of students will come to me and tell me stuff like, "Oh, just write a more optimal algorithm for processing. Like you can, instead of using Python, use C programming language. It's faster, so we can." But that's not. We aren't talking about processing a bit faster. We aren't talking about processing a single temperature probe and adjusting the temperature. We're talking about adjusting tens of millions of temperature probes, right? We're talking about like if you have a massive hotel with 1,000 rooms, and with in that 1,000 rooms in that resort, you have 5 individual temperature zones. So you have 5,000 temperature zones, and you want to process that all the time. You can't write an algorithm that's fast enough to process that without using more compute power, or without parallelising that, or something similar that you may have heard of if you are into if you're in Introduction to HPC class by colleague Bogdan. But that's essentially the problem here. You need more powerful computer. You can just optimize the algorithm because the amount of data is so high. So this is basically an illustration. So for if you have batch processing, you are storing the data somewhere, and when you collect a certain amount of data, or once every certain amount of time, you're going to grab a part of the data and process it together to determine something. With data streaming, you're going to get data from the individual sources, one after the other, and process it essentially one by one, right? Serial. Of course, usually we will have this data, as mentioned, parallel. You have this process parallelized to allow you to speed it up. So essentially, as I said, batch processing has the benefit of not needing to be immediate, so you can process large data sets over a long period of time, right? While stream processing needs to handle data very quickly, because if you're handling it too slowly, you're going to basically, if this is a road, if this is like a gate, you're opening the gate to let the cars pass by. If you're not opening the gate fast enough, if you're not doing your processing fast enough, you're going to get a pile up of cars here. And again, with data handling, batch will accumulate the data as shown here and then process it slowly, while with data streaming, you don't have like data stored anywhere. It's just being processed and stored somewhere later on, or insights are derived or something. Batch will have a high latency, as mentioned, because you have a fixed time interval that you're doing the process, and your latency is at least equal to that time interval that you are separating it, while streaming will allow you to do it with significantly lower latency relative to batch processing. Because you don't have to, as I mentioned, because you don't have to do high-speed stuff. Batch processing is usually simpler. You don't care about your algorithm not necessarily being fully optimal or something like that, because it's fine. You're going to analyze it. It will take time. That's something that I tend to argue with people, who aren't into machine learning, especially when machine learning was newer. People were like, "Oh, why aren't you? It's a lot of calculations. Why are you using Python instead of using something like Fortran or C, which is like a faster programming language?" And I was like, "Well, no one cares. Like it's so much work that saving 1 millisecond in a loop won't do a difference. It's the difference between training an algorithm, training a model for 21 days or 20 days. Like, who cares? That's batch processing essentially. We don't care about that small difference, but with streaming data, we have to care because we need to be fast enough. And again, I mentioned scalability is going to be something that we'll be mentioning a lot of times. What do I mean by scalability here? Well, it's much easier to scale. If you have something like this, batch processing, you can easily scale it. You can add more data storage, you can add more calculation units and do it, or just increase the time it takes to calculate. With increasing scaling streaming data, it's possible, but you will either need to parallelize the streams, so we have multiple parallel streams going, or you will want to essentially buy a much faster computer, so you can speed it up and go even faster. Okay, so the next thing we're going to discuss when it comes to these are basically two basic types of processing that I wanted to discuss with you, that I wanted to show you. They don't exist just in big data. They exist in different types of different approaches. Whenever you're processing data, you can either stream it or do batch processing. Even something simple like using a USB stick, that stream versus batch. There are a lot of examples that we can go here. So it's just two different base approaches that I wanted to show you here and share with you. The one algorithm that we want to discuss that's basically key for processing large amounts of data. It was essentially revolutionary as a part of HDFS, not HDFS, Hadoop in general, not just the file system. That was developed by Google, is called MapReduce. It's an algorithm that's very famous, very good, and that's very famous, very good, and it's essentially basis for for using big data and processing big data today. So what does MapReduce do? It consists of two parts. It's very simple. It does a mapping part and does a reduction part. And you can use it by, it's very good, very scalable. Let's talk about it more. So you have two parts. You have a map function. What does the map function do? Map function processes input data and splits it into key value pairs. What are key value pairs? It essentially, just gives any piece of data, it gives it a unique key, right? So as I mentioned, if we have a population of a certain country, let's say Croatia, and you have all the names, you have a data vector, you have, for example, my name, my first and last name, my address, my employment status, whatever information you have about me, the map function is going to assign to me a unique key, right? There are mathematical techniques that you can use to assign unique keys. If you want to look at them, the two I know are UUID, unique identifier, and GUID, globally unique identifier. That you can look up. There are mathematical techniques that guarantee you're getting like a unique generative key. And one thing that, even this example with people where, for example, in Croatia, we have something that's called the personal identification number. You probably have something similar in your country. That is essentially the key for all the values associated with me. This can be done via, I mentioned this, separate algorithms that are that enable us to generate unique keys no matter what, is because when you're using that sort of an algorithm, you don't need to check what's happening on the other data. You can split data into chunks and just work on, analyze it separately, right? And assign that keys to the values in your data set separately. The key value pairs are then shuffled and sorted to make sure that everything is ordered. And in this, mapping process, you can also apply any filters, transformations, computation that you want to do. For example, in my example, like you can change, like you can capitalize the last name if you want to indicate that's the last name or something like that. Reduction then takes that key value pairs that we did, that we processed, that we may have transformed in some way, and it aggregates them in some way that we defined. Whether that is by summing, whether that's averaging, whether that's combining data types together. Essentially, the goal of it is to reduce the amount of data. Right. So let's say if we have like a list of a ton of people, and my name Sandy Baris Shigota is in different, in that list appears in different contexts. Yeah, it appears in the context of me being a student somewhere. For example, just at this university, I'm a student. I'm a doctoral student, but I'm also an employee here. So something that a reduce function might do is combine the information for me as a student that says like which classes I'm taking and what I'm doing, and combine it with my employment information about which classes I'm teaching, for example. That's something that can be done. Why is this so important? Why do we want to have this MapReduce? Because a lot of times you want to combine data. A lot of times, for example, you're going to have sales. I'm going to go back to sales as an example. You have billions of sales across a certain period, and you want to figure out, okay, where do we invest more money in marketing? Which countries are our main competitors? With MapReduce, first I'm going to split the data set however I want, however is nice for me because of my computer architecture that I have. I'm going to take the values connected to it and basically assign key value pairs to them. And I'm going to extract information. What information am I going to extract? I'm going to extract information about country. Then I'm going to tell the reduce function. I'm going to have it. I'm going to write program a function that's going to take that information, and for each country, right? Each unique country that as indicated by the key, I'm going to combine it. And I'm going to, for example, sum it. At the end of it, I'm going to have the information, right? I'm going to have the information on how much each country spent. So again, I'm taking all the sales. For each sale, I'm assigning it a key that's unique, but it also has an indicator. For example, it might have something like your vehicle registration, depending on where you're from, like your vehicle registration probably indicates which country you're from. At the start, for example, it has SRB for Serbia, PL for Poland, HR for Croatia, right at the start. So and then it has a unique car registration after that. So that's an example. Then I can take every key that starts with SRB or HR and just connect it, together, sum it, and I know all the sales that exist there. If because I indicated that with key value pairs and my reduce function combined that. So now instead of having a 10 million sales or something that I want to come through, if that's what I'm curious about, sales per country, I have just the number of countries at this result, which might be 5 or 6 different countries. So I reduced 100 million sets of data points. I reduced to 5 or 6 countries where I have sales in, because that's the information that was pertinent to me, that was important to me to extract then. Another example, it's so let's talk about how the data flows in the MapReduce algorithm. Essentially, input whatever that data set that you have is split separately. It's mapped using that algorithm and then sorted and sent to reduce task. Why is it sorted? Well, because again, as I said, it's sorted by the key, and if the key indicates, for example, if I designed my map algorithm so the first 3 letters are the code for the country, right? Then I can sort it by that and have all the data for separate countries sorted. If you are a computer scientist, you will probably figure out this is this is a heap sorting algorithm that is being used here. So essentially, this is what happens. We are taking data. We have a big mix of data here before. We are splitting it into subsets. Then we are organizing it by a certain key, for example, a country or which sale originates from. And then we are combining that. This is that shuffle. Shuffle is actually, it's maybe not very indicative. Maybe it's called shuffle because it shuffles the data, but it actually orders the data into given groups. And then we can when you have all the information of one type, we can do certain processing. So for example, let's say I want to figure out, the average horsepower per car. I have a list of all cars. I split that into different subsets so I can process it on different computers to make it faster. Then again, we're talking about a lot of data, so splitting it and sending it to separate computers, especially using something like HDFS, where this is done automatically in background, isn't a big problem. Then I'm going to split this by different. This is going to be BMW. This is going to be Audi. This is going to be Mercedes, and so on. Right? Different Skoda, Volkswagen, whatever. And we are going to combine all BMW information here, all Mercedes information here, all Audi information here, and then I'm going to calculate the average horsepower based on the data that's in here, or in here. Right? That's the point of MapReduce algorithm. It sounds simple, but it's such a great approach for processing a lot of data, massive amounts of data in parallel. And one example that is also like using, if you aren't quite certain, right, how this works is, imagine that if you have some coins in your hand, you have, like for example, you have euro coins, and you have a bunch of them, and now you want to figure out how much money you have. and you dump them, what most people do is you are going to take, okay, I'm going to take €2 coins and separate them. I'm going to take €1 coins and separate them in a separate pile. And then I'm going to take 50-cent coins and separate them in the third pile. And then 20-cent coins, 10-cent coins, and so on. So I'm creating a pile of different types of coins, and then I'm separately counting each pile of coins to figure out how much money is in each pile. That's what MapReduce does. It takes a bunch of coins, right? It grabs a fistful of coins, because it's easier for you to process. If you have like a big box of coins in front of you, you grab a fistful and you're putting all €2 coins, €1 coins, and 50-cent coins on separate piles, and you repeat that with all different, because we're talking about parallelization. People who are doing this, this will be other people who are doing it, splitting it. In reality, it's actually computers. But for our example, I'm grabbing a fistful of coins and sorting them, and two of my friends are also grabbing a fistful of coins and sorting them. And then each of us can grab one of the piles, count how many €2 coins are there, how many €1 coins, how many 50-cent coins are there, and then based on those counts, we can determine the actual amount of money in that pile of coins. So that's another example of MapReduce. It's very, very widely applied. For example, just transforming different types of data and analyzing it is extremely popular. Same for searching, building indexes for searches, grouping stuff so you can more easily search, adding metadata information, processing vast amounts of logs to see what's going on, what's happening, how often errors happen, because you can split. If you have a log, if you have like you're compiling a piece of code, you have just normal information, warnings, and errors that you can split and analyze when it happened, why did it happen, etc. And machine learning can also be done like this. When you have extremely large data sets, you can split the data set, and for example, you can split it into different parts, and then you have a model for one type of operation, second type of operation, third type of operation. We're talking about, let's say, a machine. You may have like how your car behaves between 0 and 2000 RPMs, 2000 to 6000 RPMs, and above 6000 RPMs. And you can train that separately and create an ensemble model at the end. So as I mentioned, Hadoop is usually what's used it's what made Hadoop famous, what made Hadoop interesting. Was application of MapReduce automatically, almost automatically across the file system, HDFS, right? Because you can very easily, with this illustration, you have very easily already have nodes that you separated stuff into that you can go on and utilize. As I mentioned, Yarn, that yet another resource negotiator exists that helps you actually manage these separate processes. And again, it's used usually when we're talking about data, big data. This type of algorithms is usually used to perform ETL, so extract, transform, and load the jobs. Because if you're loading something if this end is a data warehouse, a table somewhere, you can easily do that transformation here on separate data parts. Just general batch processing and data warehousing. So what are the main benefits of it? Well, first, it's infinitely scalable. As many nodes as you have, that's how you can split. Again, this splitting does come with certain computational cost, yes, but if you're using something that's already built for that, like HDFS, that cost is negligible compared to processing power it takes to actually process the data. So it's very easy to process it, to split it and process it. Again, if fault tolerant here refers to a fault in the machine, if one of the machines breaks, if this one nice. We are just losing this chunk of data, right? We aren't losing all of the data, and especially when we're talking realistically, when you have hundreds of computer nodes processing something, if you lose one data, you're using 1% of data. It's not that big of a deal if you do end up losing it. You can parallelize that. Again, if you are in the introduction to HPC class, you talk about parallel processing and how that, and it was shown to you probably already how significantly that speeds up computation tasks. And finally, it's very flexible. I gave you a couple of examples I came up with just while talking. It's very, very flexible. Can be applied in a lot of different cases. As all there's a term. There's no free lunch. Nothing is perfect, and MapReduce is also far from perfect. First, it has extremely, extremely high latency. Um, Again, there's a lot of work. Mapping is computationally expensive. Uh, you have a lot of, if these are separate nodes, separate computers, there's a lot of data traffic happening here over your network. It's not, it will introduce a lot of latency. Uh, Again, MapReduce jobs when you're programming them. How are you going to test them? You can test them in a real environment. Unlike, for example, a machine learning algorithm, if you train it for, if you check the data set is structured. If you check if your code works on 1% of the data, is going to work on all of it. With MapReduce, that's not a guarantee because you can't check all the data in advance, right? And you can have some errors. For example, you can figure out that not you can't uniquely generate key value pairs. You can't separate them. There are many more elements. For example, I used the example with coins. What happens if there is, I'm counting how many euro coins I have in a pocket, and I happen to be in Serbia, and I have a Serbian dinar coin in there. Obviously as a human, I'm just going to be like, oh, cool, put it to the side. But with something like MapReduce, the algorithm won't know how to handle that. It can generate an error and fail, right? And again, some I mentioned before, they can be used in machine learning by splitting it, but you can't use the principle by itself, because why it doesn't allow for iteration. You can't go from here because you already have the data sorted. You can't really introduce looping or something like that into MapReduce. So you have, so that's the one of the problems with MapReduce. Okay, so I talked about the difference between batch processing and batch processing and stream processing. So if you haven't figured it out from me talking, essentially when we're talking about batch processing, we are talking about using MapReduce. That's one of the most common algorithms used today for batch processing. So that's why we covered it now. We're also going to cover the real-time data processing. But before we move on with that, I'm going to just give you a 10-minute break just to take a bit pause. So I'm going to pause now and we're going to continue at 11, so in 10 minutes. Okay. Hello, everyone. Let's start with the second part of the lecture today. So, we are talking about real-time data processing. Let me just repeat. So, we defined a bit better what parallel processing and sorry, not parallel, but batch processing and stream processing is. And we talk about MapReduce, which is the algorithm that's very commonly used in batch processing when you have a lot of data that you need to process that was collected over a certain period of time, and you needed to process that data separated into certain key value pairs and then do some sort of calculation on it. That's something you may want to use MapReduce for. Okay, so let's talk now about the opposite thing. Let's talk about real-time data processing. Uh, So, as I said before, in real-time data processing, we want to uh, do something. We want to continuously analyze data. As the data arrives, we want to immediately process it, right? Think of it this way. Batch processing is something like you have your car parked. You have a car park and you're a mechanic and you want to process fix those cars, check them or something. You're going to check them. Oh, today I'm going to check these 5 cars. Tomorrow I'm going to work on these 5 cars, and so on. While real-time data processing is something like a highway toll booth. When the car arrives, you need to do something with it immediately before it moves on. You can't process it, in a batch. You can process 5 at a time or something like that. Again, a lot of stuff like personalization, monitoring what's happening in your network or with your sales or stuff like that is requires you to do real-time monitoring. Again, you can monitor and check what's happening with stuff if you are doing it in real time or near real time. Again, for the computer scientists or computer engineers in audience, I know that real-time processing is something that's defined as a difference between real-time and computer time usually. Again, this class isn't as heavily focused for people, in computer sciences and stuff like that. It's written to be a bit more general. So when I'm using the term real time, I'm not using it in the context of real versus computer time and real time programming. That's very complex. I'm using it more colloquially, like, we're getting stuff as it arrives. We aren't necessarily doing the proper real-time programming, right? Where we want to have zero latency in processing, or we tend towards having zero latency in processing. There can be some latency introduced by real-time data processing. It's not so key to have none, as long as it doesn't introduce issues with us where the data is getting piled up too fast. Okay, so just a little clarification for you who are more familiar with computer engineering. So what are the challenges with real-time data processing? Well, volume, velocity, and variety of data. Again, as I mentioned, with big data, you have a lot of data. It's arriving very fast. It's not a problem. Processing a lot of data. If you get data point each second, a second is a lot of time to process something, right? We're talking about computers. So once a second is the problem. Once a millisecond, that's a bigger problem. And the third thing is variety of data. Again, we're talking about big data. We're talking about multiple sources, usually, and that means that not all the sources will be formatted equally. As I said, again, I'm reminding you of the example. If you're getting, your bills from somewhere, maybe some will be handwritten, maybe some will be in text format in an email, maybe some will be in a PDF invoice. There's a lot of different possible examples. So why do we need why do we need this in addition to just having why do we need real-time data processing? Essentially, we need to, as mentioned already, when you have big data when it's being processed immediately, you open up a lot of doors. You can actually monitor stuff. You can immediately tell people what's going on. You can immediately inform people that there's possibly an error, or hey, this isn't selling. So one example is, for example, let's say you have a sales platform for something, and you notice that a certain product that you have is underperforming. You can automatically, right, without even human input, you can automatically promote that product more. Maybe place it so it's first when you land on the page when your customer opens your web page for sales. That's the first product they see. Maybe you can lower the price of it, increase the sales numbers on it, so it's a bit so it's better, more attractive to the customer, and you can do that automatically with real-time data processing. That's an example of it. If I mentioned the fraud detection, you want to detect fraud as it happens immediately, react immediately, lock down the credit card or something. You don't want to do it 6 months later. It doesn't have a lot of, benefit then. Okay. So again, I'm just going to play the overviews here. Real-time processing is computationally real-time data processing. Again, I'm not even talking about like actual zero latency processing or extreme low latency processing. I'm talking about something that appears to be done in real time. It's much more complex than batch processing with MapReduce. Like MapReduce can be directly, explained using somewhat simple examples. The algorithms used in real-time data processing are more complex, and when we were creating this lecture, we deemed them, in general, most of the partners to be a bit out of scope for the people here, especially, people who are coming to us from economics or, medicine and stuff like that. It would be a bit too intensive to try to explain them. So instead of that, I'm just going to give you overview into platforms that can be used. So if someday you're in a meeting somewhere and you're building, you're someone is, discussing about maybe you want to real-time process some information, maybe patient information as it comes in and so on, that some certain elements, certain tools exist that can help you accomplish this, and then you can go in that direction with your engineer that is assigned there or something. So one of the tools is Apache Kafka. Kafka as the writer, right? Kafka is a distributed event streaming platform. When I say event, I don't mean event in terms of a boxing match between Jake Paul and Mike Tyson. I mean a computer event, right? Like something happens, a purchase has been made, a credit card has been processed, a patient data has been uploaded to the system. That sort of event, right? Okay. It's used for building something, and this is a term that's very commonly used. It's called a pipeline. So we are using something to build real-time data pipelines. Pipeline is a set of serial processing that can be done to a data stream to speed it up, process it, ETL, run ETL on it, etc. And basically, you have your source here at the start. You have your endpoint, whether that's your machine, your database, or something. And by pipeline is anything in between that needs to happen to data to get it from your source to wherever you want it, whether that's storing it in a data lake, storing it in a data warehouse, displaying it somewhere. That's essentially pipeline. And Apache Kafka allows you to build these pipelines where you take a data source, like, for example, maybe a stream using SFTP, maybe SFTP data you're getting from somewhere, maybe is being sent via TCP or UDP, if you remember, talking from data storage and management class, maybe something like that. A data stream, you're taking it, and you can't just automatically input the data from an UDP stream. You need to run some processing on it. Maybe you'll unpack it using Python, read the data from that socket, from that port you're like open that port again, if you remember from data storage and management, open the port, read the value that's sent to you, eliminate the overhead data, maybe process it, add some information, metadata information to it, and store it somewhere. That's something that you can accomplish with like Python if you're having a relatively low speed stream. Kafka is a set of tools that allow you to do different types of processing in a fast and in a scalable way. So it can easily be scaled across multiple machines to achieve real-time analytics, log processing, data integration into existing structures, and so on. And what essentially allows you, it uses something that's called topics, which are like separate pipelines to decouple message delivery. This means that the producer and consumer of data, right? So producer of data is the person making the purchases. Consumer of data is you, right? So it's a bit opposite than the terminology that you would use in economics, where the person buying is a consumer, you are the producer. This is different because you are getting the data from them, right? So they are producing data, you're consuming the data in some computational manner. And it allows you to decouple that. Basically, decoupling means separating it and then inserting different processes in between, building that pipeline so you can process it in detail. Another option that you may use is Storm, also by Apache, which allows you to run unbounded data analysis and processing on unbounded data streams. What does unbounded data stream means? It means that you don't know what's happening, you don't know how much data is going to come, you aren't sure about the volume of data, so how much parallel lines you need in between, and you also don't know how much that data is going to, how much data is going to be generated, how it's going to look like. What Storm allows you, it allows you to be very flexible, and when you have if you're having 10 sales, you want to process those sales immediately, or you have a 10,000 sales, it's built to essentially automatically scale up to make sure that that is happening. So that's great. For example, fraud detection, you are processing credit card sales to make sure there isn't anything wrong with them, there isn't any sort of mistakes or mistaken faulty credit cards, buying stuff that wasn't authorized by the user, something like that, or just general errors with purchases, etc. You are going to have the same amount of data each time. At 2 a.m. you're going to get many less sales than at 5 or 6 p.m. when people are going shopping, right? Same goes, right now 11 a.m. most people are working. There's less streams, so there's less credit card sales being made right now than it will be, at 5 p.m. after people get off work. So that's something that Apache Storm can handle. So how do these two work together? Essentially, Kafka deals with being a message broker. So it takes care of storing the data, transforming the data, getting the data. You can think of it in a way like having a secretary, right? And your secretary, they receive your mail and manage it before they give it to you for processing. Storm will take care of that processing. That is you, except Storm is great at, as I mentioned, processing, splitting, creating multiple parallel streams to process data, etc. But it does it on data that was previously prepared in some way, figured out, and gotten ready for processing. Basically taken care of, as I mentioned. If you remember talking about protocols, if you remember UDP, you're going to have some additional information, some overhead, especially with especially if instead of this, UDP you're using TCP to send data, you have a lot of additional information like who is the source of the data, you want to split that sort of information apart. We're talking about the big data, we're talking about different sources. So you're getting a message and you want to extract information from it because everyone has different capabilities, basically different sources. Maybe you're getting some data in emails, maybe you're getting some data in PDFs. You want to extract all of that and store it, and get it ready for processing. They are used, as I said, Kafka will handle that high volume data ingestion, getting the data in your system, just receiving the data like your secretary would, or you can think of it as your if you have like a mailbox, that's what Kafka is, and it handles receiving a lot of data, while Storm is actually reading, actually processing the data in a parallel manner. And you're usually going to want to introduce two. That's why Apache developed them as is. Yes, there are some cases where you might want to use Apache Kafka but not use Storm, or vice versa. Maybe in a data lake you don't need to process data, you want to just dump raw data. Then you can just use Apache Kafka to help you get all those sources inside again. So let's just again repeat. Apache Kafka, you're getting mail from a bunch of different sources. Apache Kafka is going to be your mailbox that's going to enable you to get that mail in one space, no matter who is sending it to you. While Storm is actually going to help you read it. You can think of it in that way. Okay, so let's talk about what is analytics, what types of analytics exist, because that's, as I mentioned, one of the main points in big data itself is going to be why are we collecting that data, while we're spending time, money, programmer resources, developers, paying them. We need to get some value out of it. How are we going to get some value out of it? Once we have collected that data, processed it, we have it stored nicely, we have a lot of it, we need to analyze it in some way. We need to actually benefit from it, and we can't benefit from it unless we do some sort of analysis. There are three types. We're going to cover them: descriptive, predictive, and prescriptive analytics that will allow you to help you, whether it's usually we're talking here about business support, decision making, strategy improvement. Again, it can be applied in medicine, it can be applied in science, but usually we are talking about business organizations, sales, production, etc. So what are descriptive statistics? Descriptive statistics will cover past data, provide you insight into what has happened. We had a sale last month, which items did we sell, which items we failed to sell, which were fine, which weren't fine, we had a marketing campaign. How did people react to that marketing campaign? Did we get an increase? Didn't we get an increase? That's an example of using historical data, data that has happened, to sit down and figure out what was going on. Was something successful? Are we having troubles? Are there any trends, and what may cause them? Maybe we have less sales in the second quarter of each year for the last 10 years. Okay, that may indicate something is causing that, because it's a repeating pattern and so on. That's something that we can do. Usually you will use business intelligence dashboards. Dashboards, as I said, are just I talked about it in data storage and management. It's just a program that visualizes data, using graphs or images or something like that. Predictive analytics, on the other hand, is when you want to, you aren't looking at past data figuring out what happened. You're looking at past data and figuring out what will happen. So again, I use the example for the last 10 years. In the second quarter of the year, we get lower sales. using descriptive analytics, we want to figure out what's going on here. Why is that? Why is that happening? Why are we losing sales in the second quarter of the year? Predictive analytics are, on the other hand, used to say like, oh, next we can expect to have a poorer second quarter this year because this and this. It's usually, this is a simple example. It's usually not that simple because there are a lot of outside factors, not just historical trends that we are looking at. But for example, we can look at customer data and saying like a lot of our customers are, from IT sector, and we know that this year there were a lot of layoffs in the IT sector. So it means that probably not many people will invest money. Our main customer group has a lower sales power, right? And that's a sort of predictive analytics where we're looking at the data that we have and focusing on trying to figure out what will happen. Usually what happens here is we have machine learning performing regression tasks, time series analysis, where we basically can tell it, hey, how is this with time series? If we have a graph, we want to say how it will continue. With regression, we have a set of variable inputs and we get an output. For example, we get something like another example here that we may use. We can create a model for car insurance, and we can figure out the likelihood that the person is going to be in an accident. So we can input certain information about that customer, like their age, what car they're driving, how much horsepower the car has, whether it's a new car, whether it's an older car, and so on. And we can get a value that tells us whether we are what's the likelihood of that person getting into an accident. An 18-year-old with a 600 horsepower car is probably more likely to get into an accident than a 45-year-old with a 60 horsepower car, right? And so on. That's regression, right? That's where we want to, based on certain values, we want to figure it out. Time series is when on just historical data, historical movement, we want to figure out what's going on. That is very, very usually if you're dealing with machine learning in business, on business data, not in computer vision, CNNs, and stuff like that. You are going to be talking about doing predictive analytics because you want to figure out what's going to happen. And regression is very interesting here because you can adjust different incomes and see what's going different incomes, different input variables, and see what's going to happen. And that's what is called prescriptive analytics, where you want to recommend actions. So if I have, for example, if I'm doing a regression, I'm anticipating sales on a product, and the inputs for that product are going to be the cost, the rating on the website, and the amount of money that was spent in advertising it. That is going to, I have a model that's predicting sales based on those numbers, right? Prescriptive analytics is going to take that and it's going to test those values and examine them to see like, okay, if I increase the money put into advertising, how is that going to affect sales? Is it going to increase sales? Is it going to decrease sales because people will be bored and annoyed at seeing my advertisement constantly? If I introduce, if I lower the price of the product, or if I try to contact previous purchasers and ask them to rate the product and in that way increase, how is that going to, what should I do in order to try and generate more sales? Again, I'm using a simple example with 3 variables, something simple, but usually you will have much more inputs for this, and you will be running, for example, I will use the example of my PhD. I'm doing robot optimization, energy optimization. I have 20 inputs, right? And those 20 inputs are, and I have 100,000 data points. So you can't analyze it as easily like this when you can, like with the example that I gave you, it's very simple, and you're thinking, oh, like, of course, if I lower the price, I'm going to increase sales, etc. But that's just an example where you want to, you want to analyze how each individual input, right, is going to influence the output. You want to test it. And from my experience, business people, businessmen, especially like C-suite executives, higher level managers stuff, love when you give them a nice dashboard, and they have like a little keys they can turn, push forward, push down knobs they can turn virtually, and it's going to give them an output out there. So if you're ever, need in a position when you need to make sure that a CFO is happy with an analysis, don't give them a computer code where you can adjust values. Give them nice sliders and knobs they can turn and play around with and get different inputs, and they'll think you're a genius. Just a piece of advice for using that, and then they can do prescriptive analytics on the model that you developed, and they're going to be happy. If there are a lot of inputs, you will probably want to use something else, such as optimization algorithms, Monte Carlo simulations for simulating thousands of points. You can run decision analysis. Yeah, there are a lot of techniques here that you can do. Again, this isn't about machine learning, but again, this usually optimization is done with artificial intelligence, evolutionary algorithms, genetic algorithms, and subsets of it, like mimetic or logical algorithms, decision analysis, and input analysis is usually done with something like random forest or correlational analysis when you want to see how do the inputs affect the output, right? Usually, you want to combine all three types of these analytics. You don't want to have them separate. Again, prescriptive analytics generally can be done without you first doing predictive analytics. That's the obvious part, right? You can't have a prescriptive model where you test the different stuff if you didn't develop a well-functioning predictive regression model or something like that. Descriptive statistics, on the other hand, are also necessary. We want to analyze past data, we want to figure out what's going on, and they're usually integrated. If you're developing a predictive model, you're developing it on historical data, and you want to see if it fits historical data. You're going to use this data to verify your predictive model. So that's one example of using this in combination, and generally you want to use them in combination. You can't not use them in combination in most cases, because you're going to need all three. And people are going to want, when you're running analysis, when you're running like how business is acting, how it's performing, you want to look both historically and you want to develop models on it. And this, as I mentioned, is usually done using machine learning, using artificial intelligence today. Why? Because you mentioned this, you had introductions to DS and AI and so on, but machine learning will essentially enable you to get what machine learning does. It learns from the data. It creates models of the data or the statistical distributions within data. But instead of using standard statistical descriptors and stuff like that you can use a smaller data sets to indicate stuff better, machine learning can handle vast amount of varied data, and because it does a multivariate modeling, where it creates models based on interconnections between all variables within the models. It can uncover some hidden patterns, hidden relationships between those variables. You aren't figuring it out. You have supervised and unsupervised learning we talked about. You have reinforcement learning. Again, I'm not going to go in depth about these algorithms. It's not really the point of this class. There are other classes that go into this more, but essentially what you need to know in terms of big data is machine learning is very, very commonly used to create those models, especially for predictive and prescriptive analytics. And again, fraud detection, recommendation, expert support systems, predictive analytics, as I said. When we're talking about machine learning as a source, basically big data is the source of data for machine learning to basically generate models. This is what we want. This is what machine learning engineers love: big data systems, because we love having hundreds of thousands of data points that we can analyze, because with machine learning, the bigger the data set is, it's covering the higher quality the model is going to be, because it's less likely there is a bias introduced in it. It's less likely there are errors introduced in it. It's less likely it's not covering some sort of behavior. Like if you're trying to predict sales and you're using data from November, you try to model that, to create a model for December where everyone is buying stuff for Christmas, is going to be completely wrong, right? So you want to get the data not for just 1 year, you want to get the data for 10 years and analyze all of that when you're doing machine learning, and that's something that big data enables you. There are other artificial intelligence techniques that aren't necessarily fall under umbrella of machine learning. We are talking about mostly today, especially again, we started preparing this course a while ago, so it's not directly included here, but something like ChatGPT, right? Where you can use, something like natural language processing to figure out stuff like reviews, because reviews, just ratings like 1 to 5 aren't necessarily great. They can be, hard to figure out because, you will get people who will be like, I bought this toaster, it caught on fire and it almost burned my house down, 4 stars. And then you're going to have someone who's going to be like, the box was slightly damaged on the outside, but the product was awesome, but the box was damaged, 1 star. Right? So using NLP can provide you better insight because it actually looks, something like ChatGPT. If you give it, if you feed into it, a bunch of reviews and tell it, hey, is this a positive review? Is this a negative review? How positive is it? How negative is it? It's going to be able to do that for you, and that's great. And it's a better indicator than just looking at, star ratings or something like that. Then, deep learning is just a subset of machine learning. We're using a bit more advanced algorithms, larger algorithms to simulate it, right? But usually today, the biggest step forward here is natural language processing, because with stuff like with large language models such as ChatGPT is, the example you probably most of you are familiar with. It helps you get some really important information out of what exists for you. Automate this usage of AI in general. It allows you to automate tasks, to determine how stuff is done, how stuff is pushed, which class it belongs to, where you're going to store it, etc. Like we talked about MapReduce, generating keys. If you want to, generate it on different classes, yes, you can do that using AI classification algorithm that generates that keys for the map part of the MapReduce algorithm, for example. But again, today, what we're mostly doing, chatbots, because, for example, support system not only can use a large language model, like again, I mentioned ChatGPT as an example. Not only you can use that to be the chatbot, right, to provide answers. This is something that's called a specific, when you're specifically targeting, it's called a RAG, right? And you can use that So RAG stands for retrieval augmented generation, when you want to generate a specific part of for LLM or something specific, like phone support or something like that. The phone support chatbot, can not only provide answers to your customer, it can also determine were they happy or not with the replies. Hey, did they seem happy? Did they not? Hey, was this complex? Do you think this person was well versed in technical knowledge or not? And that's something that you can program your chatbot to, like, as soon as the conversation finishes, it can automatically generate all that information. So you're killing two birds with one stone. You're killing both the support, the level 1 support, and you're doing other information, and you're classifying that customer. So saying, like, hey, this is a customer that isn't great at providing information, and I, as a chatbot, wasn't able to figure that out. So I need to move them to a level 2 agent, which is a real person, to discuss with them. Great. If that happens 2 or 3 times in a row, I can just mark that customer to directly send them to a level 2 to resolve their issue faster. Right. That's something that can be automatically used, and that's something that a lot of money is being invested recently into using NLPs in that way. Okay, another term that you have heard mentioned around big data and stuff is data mining. What is data mining? It's when you have a ton of data sitting in front of you. You want to figure out, some patterns. You want to figure out some trends. You want to extract knowledge. You want to extract information. What do you do here? What are the techniques here? There are multiple of them. Whether you want to use statistics, whether you want to use machine learning, some database specific algorithms. Basically, your job is here, is knowledge discovery in databases, KTD. That's something that, if you ever hear someone say they are a KTD engineer or something like that, they are dealing with data mining. So the idea is, if you have a lot of data, you want to take the data and get a valuable insight out of it. Again, as I said, if you don't get valuable information, it's useless. Data is useless. Just a ton of data on its own, even if it has useful insight inside them, if you don't extract it, people won't be able to act on it, right? Your C-suite executives won't be able to decide how to invest money, how to strategize the company, unless they have insights given to them by this. You can also be, and the data, as mentioned before, improving decision making, predictive future trends, etc. This can be used, and this can be done everywhere where you're collecting data. When you have a bunch of data stored somewhere, you can use data mining. Is just a general catch-all term for extracting information that can be processed by humans easily. Easily, I mean something in terms of if you do this, this is going to happen. If this, then that type of procedures. So what falls under this KDD process, knowledge discovery and database process, in data mining, essentially. So there are multiple steps, multiple parts, multiple things that happen here. First, we have data cleaning. If some of you are listening to the practical data collection class, you will remember we talked about outliers and stuff like that. You want to remove data that is inconsistent. You want to remove data that shouldn't belong there. Data that is obviously errors and stuff like that. You want to remove it. Then the next step is that you want to integrate the data from different sources together in the same manner to make sure that all of your data is full, whether it's in a JSON, whether it's in a table, SQL table, or whatever. You want to combine data from multiple sources so it appears to the people going forward that it's a single data source, right? So whenever the next person comes along, or for these other steps, they have a single table they need to analyze. Then we have data selection. that is identifying the data the cell want for the analysis. If you have patients somewhere, you have maybe 1 million patients, but not all of them are in the group that you're interested in. Maybe you want to see how someone behaves under a certain medicine. Was there an improvement? So you're going to select people who took that medicine, and maybe some people who haven't, to use as a control group to see what was happening with them. Maybe I told you in other classes I also do astronomy as a hobby. We have cameras that are collecting data. If I want to check, for a certain phenomena, I'm going to select nights where that phenomena was more likely. I'm not going to analyze billions of videos from across the world, right? Uh, so that's data selection. Data transformation is converting data into appropriate formats for doing the analysis you want to do. So if I know that I'm going to be doing machine learning on it, I'm probably going to convert it to a NumPy data format or something like that. That's beneficial to me because it's faster to do machine learning on it and so on. And finally, we get to the data mining process where we apply actual algorithms to extract information, extract patterns, whether that's time series analysis, whether that's regression analysis, clustering, classification, whatever we're doing here. This is the step we're actually doing it after taking care of all of these. And finally, we have evaluation. When we figure something out, we figure out that, hey, if I increase this variable together with this variable, this happens. That's evaluation. That's where we want to figure out what insights are valuable, what aren't. And finally, we want to present what figured out in the usable form. That's why I said people, C-suite, high management, they like having nice, turn this knob up, the information changes, turn this knob down, the information changes. They don't want numbers. They don't want code. They don't want a massive Excel file. They want a nice little graph that shows them like, hey, this is the actual situation. This is how our algorithm predicted. So you can see that these two overlap, right? And this is something that was, introduced to me like back in the day when I was a student, and I was working on a project for someone, and I walked in and I presented him the project. I'm under an NDA, so I can't give you the details on that project, but basically what I showed him, showed that person who hired me, was like a bunch of numbers on the screen, like matrix style going down, and I told him what the numbers mean, right? And he just nodded. He told me like, that's great, but let me give you a piece of advice. I understand he had the background in computer engineering. That is great, but if you came with this to a banker, or you came with this to a manager, they wouldn't understand. They would just see numbers on the screen and shut down, right? If instead you showed me the picture that was being processed or something, and you visualize something like that, it's extra work, but that's what would actually mean something, and people would be impressed. And that's something that I do a lot today. When I just have a student right now who is doing like detection of certain elements on the image. That's a project that we give to different, with different data sets to different people. And I always tell them when you're presenting, when you say something like, I had an IOU score of 0.85, and I had the map from 0.5 to 0.95 of 0.46. It just starts sounding like noise, right? But if your last slide is going to be an image and you're going to show, hey, this is an X-ray of a person's chest. Here is where we detected a tumor. You can see how our algorithm, draws a bounding box around the affected area. Or this is a steel plate, and we have detected the damage here, and our algorithm like draws the area that has been affected. That's a massive impact. That's what people see and go like, oh, okay, I get it now. That's the point of the algorithm. Look how well it works, right? So that's the point. Knowledge needs to be represented in a form that's easily digestible if you wanted to use it. So one of the examples that I said is classification. classification is when we have data, we want to classify it in one between two or multiple classes. So for example, if we have something like I mentioned a lot of times fraud detection, or we have here email spam detection, medical diagnosis, credit scoring. You're going to have something like this person is credible. You can give them a credit or not, etc. For medical diagnosis, you will have a person is diseased or isn't diseased. You're going to have whether an email is spam or not. Or for example, if you're using Gmail, right, you know that you don't just have spam, not spam, but you actually have a ton of different categories in there that it can be sorted automatically. So, for example, I have my mail gets classified between spam, primary, promotions, social networks, updates, and forums, right? And those are the categories that I have. So you don't have to have two classes, you can have multiple classes. It's a supervised learning technique, right? So you need to have data that you already know which class it falls into. This is usually done manually, right? At least in the start. How are you going to do that manually in big data environments? Well, you're going to create a model. You're going to generate some data manually, then create a model that you're going to use to automatically annotate the data. You're going to check the data manually, but checking is much faster than classifying. And then you're going to go and train a model that you can use later on. What algorithms are used here? The series of trees, bias, support vector machines, multi-layer perceptors, neural networks, etc. Again, there are classes in this course that deal with this. I'm not going to go into these algorithms in detail. What is clustering? Clustering is, in my opinion, much more useful in data mining because it's unsupervised. That means that you don't need to have labeled data. You don't need to have someone go through your data and say this is spam, this isn't spam. It can automatically group data on data similarity. So usually just tell it, hey, find me how many clusters of data you can form this into, and it's going to tell you, hey, I can form it into 3 clusters, 4 clusters, 5 clusters, 6 clusters with this type of accuracy, and you're going to select the one that gives you the highest accuracy. And this is great because you can cluster. For example, this is very common in very common in social media, right? Or in sales, where you want to group your customers. You can automatically split your customers in different groups, and you can address different groups separately. If you have someone who is regularly buying from you, you want to have them to stay. Well, if you have someone who bought something from you, once a year, you want to increase their purchase rate, and you want to treat those two groups differently. So you can do clustering to see how many different groups you have, and treat them accordingly. Treat them, invite them, maybe, for the person who is buying stuff constantly at your site, who is, you want to reward their loyalty by giving them a discount or throwing something extra, when they purchase something, and so on. While the person who is, you don't need to send them emails and be like, hey, come shop, because they're already shopping once a week, right? While the person who is, purchasing once a year, they know your site exists. Why aren't they coming? Maybe they forgot about it. Let's send them some email reminders. Let's say, like, you can act in a different way. Another example is, detecting anomalies, because if you have something that doesn't fit well into any of the established groups that you have, you have as I said, you have for example, students, you have students who will put in a lot of effort, do high scores. you have students who put in a low effort and get lower scores, and now you suddenly have someone who is not putting a lot of effort. For example, by effort I mean like not completing any extra work or not completing their assigned work during the semester, waiting till the end of the semester to submit it. But they are scoring well, great in tests. Maybe that's an anomaly. Maybe that's something you want to look into. Maybe they are just a lazy genius. Maybe they are cheating or something like that. So that's an example. For example, anomaly detection and image segmentation. If you want to separate like an image, here we have an image. You want to separate into different parts. For example, background versus a person. You can do that with clustering by checking the similarity of certain pixel groups. Some more specific data mining algorithms now. We have something that's called the hierarchical clustering, which essentially builds a tree-like structure that's called a dendrogram, or a tree. It's a dendrogram is just one of the titles that's used. You can create it bottom up as an agglomerative or a sum, right, or divisive. Top down. I'm going to show you how hierarchical clustering looks, so it's going to be clearer. And the benefit of this is in clustering you usually tell it how many clusters you want to have, right? How many clusters you expect. And if you actually have 5 clusters, but you insist on having 4 clusters, it's just going to generate 4 clusters for you. Again, we are talking about extreme multivariate data here, and you can figure out those clusters on your own, right? Just looking at the data visualization. So that's something that can be a problem with clustering if you have an engineer that's not paying attention, or if you're doing something automatically, right? And you set the number automatically to 4 because that's what you expect. You get something that's an anomaly, right? And you don't detect that. So, for example, you have 3 groups of students, as I described, and you have like 4th group is going to be, everyone who falls into 4th group is going to be anomalous. But through years, trends change, how people act change, how people study change, and that 4th group might generate on its own, while the anomalies would actually fall into a 5th group, right? So we're creating an error by misjudging the number of clusters. Hierarchical clustering doesn't have that problem. It doesn't need to know that, and is great for visualizing data relationships. So here are some examples: chain expression analysis, clustering documents together, analysis social networks. This is essentially how it looks like. And you can see the difference between going bottom up or bottom down. Basically, the idea of agglomerative clustering is to get different groups that you have, identify them automatically, and be like based on certain things like, okay, what are the similarities here? Well, these two have wings, so we're going to tell they're birds. This walk on 4 legs. They're mammals. Or this we can truly classify them here. They are they have more than 3 legs. They definitely aren't mammals. They definitely aren't birds. We're going to set them here, and you can basically based on data trends, separate data trends, you create clusters. Here, this is usually done in a relatively simple way. You have, if then rules. So if whatever I'm looking at has wings and 2 feet, it's a bird, right? The problem with this is, yes, you can generate some of this automatically, right? But usually it will need to be fine-tuned by people. So that's something that you need to be careful about, because people can introduce biases, make errors, and do stuff like stupid errors like, oh, if it has more than 2 legs, it's a mammal. Well, which obviously isn't true, because then spiders, scorpions are going to be mammals, right? Or it's going to be like, oh, if it has more than 4 legs, is going to be it's going to be an insect, which isn't true. Or like here, if you look at it, it has more than 3 legs. The definition that they used to create this graph was probably hind legs. They differentiated, but maybe if I was building it, if I was putting information in here and I had to put information about the bear, I would type in that the bear has 4 legs, not 2, right? And I would misclassify it. So that's the problem with hierarchical clustering. Again, no free lunch. You either can make a mistake with having a predefined number of clusters, or you can make mistakes based on the rules that are being generated here using a decision tree algorithm or your own tree that you're drawing by yourself. What other algorithms have? One is association rule. Mining, this is commonly used algorithm, is something that's called an a priori algorithm. The point is that it looks for frequent sets of items that repeat. For example, this person buys this perfume every month, and it tries to figure out the confidence, the lift, how well is the purchase being made, and figure out, okay, this person buys this perfume every month, is probably going to buy it in the future. If they stop appearing, if they stop coming here to our, if they stop showing up to our store, maybe if we send them an email that's targeted, and it specifically gives them a discount on the perfume they were buying each month, because maybe the reason they aren't coming here anymore is because they found it cheaper somewhere else. Maybe that will drag them back to our store. So that's something that we can do. And again, when I'm talking about personalizing, students sometimes get confused and tell me like, hey, you were talking about having like a massive amount, and now we're talking about personalizing something. Should we talk about groups? Well, that's the benefit of doing big data analysis. It's automatic, it's programmed, it's computers are very fast, and we can actually run this type of analysis on a personal level, that when a customer falls into a group of lapsed customers, like they aren't buying anymore, we can analyze their historical data automatically and react accordingly to try to get them back to shopping with us. I mentioned the a priori algorithm as an example here. So what a priori does, it finds frequent item sets, right, in a data set. So item set is this person purchasing this item, for example. This person purchasing this service, for example, that's going to be an item, right? First, it uses breadth first. I think you covered this in introduction to this and AI. What is the difference between searches in width, in breadth, or in depth? Basically, what it does, it tries to figure out which sets of items aren't frequent. You go over it because you don't know what frequent means, right? If you have a set of 10,000 points and I tell you something happens 3 times, the same item set appears 3 times, is that frequent? Your instinct might be, no, that's not frequent. 10,000, 3 items. But what if all the other items are unique? Then that's an anomaly that you should know that there are 3 repeated items here, right? So you can just use the rule. It essentially prunes the item set. It says like, okay, these item sets that have less than 3 repeats aren't going to be included. Let's review and so on. So here's how it looks. This is our database. We have a certain item ID, and we have some items here. So this is, for example, a sale, right? This is 1 sale, 2nd sale, 3rd sale, 4th sale, and we have we have items that were sold A, B, C, D. It can be like oil, milk, eggs, whatever. Now, on our first scan, we're going to count how many A elements there are, how many B elements, C, D, and D elements are, and we can figure out, D data set, D only has 1 set, we're going to remove it. Okay, we don't care. So now we have A, B, C, and D together that we have removed, right? Okay, because we have removed this one set that isn't that has only one, we have decided to keep 2s and 3s together. Then we move on to this and we look at combinations. So A combined with C, B combined with C, B combined with E, C combined with E, right? We're trying to look at different combinations here to see what's going on, how the sales look like, right? Because now our item set here is A, B, A, C, A, E, B, C, B, E, C, E. So we're looking at all possible combinations here. For example, we're trying to figure out if these are items, which items are often purchased together. Why? Because if two items are often purchased together, if a lot of people buy, for example, I don't know, oil and flour because they are making bread, we can bundle together oil and flour and sell them at a bit of a discount, and that's going to invite more people to buy stuff at our place as opposed to our competitors. So now we're looking at, okay, which sets exist, which sets are, what is bought often, and looking at this original database, we can see that A and B is bought together only once. A and C is bought together twice, here and here in 10 and 30. Same goes for A and D, B, C, B, E, C, E. And we're going to, for example, B and D. We have B here, E here, B here, E here, and here, person purchases just B and D. We eliminate those that were once, and now we have the item set of AC, BC, BE, CE. And what happens here is we can't combine it anymore. We have BCE as items that exist here because we can eliminate, because we have BC, BE, CE. These combinations, they attribute, for most sales, right? We have, it will include this sale, it will include this sale as well here. So as the same as we recombined the data set here, we have recombined the data set here. Okay. Again, right, this is the basic algorithm. So we break down, again, we take this, we break down the individual items, eliminate those that aren't common. Then we look at the next level, at the number of combinations, and we observe that combinations, how they are, how they exist, which aren't common, and so on. That's the a priori algorithm, and it's great when you're trying to figure out what people are doing. For example, in academia, we may do something like checking historical data to see which classes people are taking together, and figure out what classes are interesting together, so we can minimize overlap between under those classes. So if we see that, for example, in this course, a lot of people have taken big data, right, and a lot of people have taken, I don't know, supervised and unsupervised learning, we can go, okay, so in the future, we might want to minimize any possible overlap. We might check in more detail to make sure there isn't, anything special or something that's popular in European Union now are micro qualifications, where if you're, finishing your you're in your graduate course or something, and if you take these two elective classes plus this mandatory class, if you pass them, you're going to get micro qualification in addition to your graduate diploma, and that's something that exists that can be informed. With this, we can see which classes people are taking together, and that's why it's called an a priori algorithm. So we can, based on a priori data, we can figure out, so this people commonly take together these classes, so we can form that into micro qualification, so because that would benefit most of our students. As I mentioned, the regression is very common, especially in engineering. In sales and stuff, it's usually medicine. You usually prefer having a class, having this falls into this class, this falls into that class. In general, regression, I mean, obviously can happen in a lot of different examples, but it's essentially getting a certain value right outside of it. So, based on these inputs, what is going to be the temperature of an element, of the engine, and so on. There are a ton of different types. You have linear regression, logistic, polynomial. This assume a certain connection between inputs and outputs, where they are connected in a linear manner. So the output epsilon is equals to something like 3x plus 5, right? Logistic, or whether it's connected with a polynomial, or if it's much more complex with that, you're usually using neural networks, namely multi-layer perceptron is a common neural network that gets used. In addition to engineering, as I mentioned, you can use it in stock price prediction and sales forecasting. And finally, risk assessment, I used that example before. Then we also have anomaly detection, which is used to, focus on detecting errors, detecting anomalies, detecting possible issues within the elements. There are specific algorithms for this, as I mentioned them already. So, clustering or hierarchical clustering, classification, but it's focused on using anomaly detection. What is the problem here? Anomalies are rare because, if we're talking about classifying, something like healthy or unhealthy patient, you're going to have 70-30, something like that distribution between healthy and unhealthy patients. But when we're talking about anomalies, if you're talking about again, credit card fraud, vast amount, like 99.9% of credit card elements that are processed are valid, aren't fraud, right? But that 0.1% is fraudulent. Why is this a problem? Well, if you throw that into a machine learning algorithm, all right, and your test set is separated by the law of big numbers, is going to say if you randomly separate this larger data set into smaller data set, it's going to keep the same distribution, right? The same likelihood. Your test set is going to have, your test set, instead of having 50 data points that are fraud, 50 data points that are correct, that are not fraud, you're going to have 99 normal transactions and one fraud transaction. And what is the problem here? The problem is that your algorithm, if your algorithm learns, machine learning algorithm learns to just classify everything as correct, you're going to get a very nice score. You're going to get 99% accuracy, which is obviously a problem, right? So when we're doing anomaly detection, we want to evaluate the algorithms differently, right? Because we want to see how correctly, we don't care about how correct they are on getting normal operations, classifying normal operations. We want to see how correct they are. We want them to detect every case of the fraud. And if it doesn't detect the case of the fraud, we want to use metrics that punish them, such as the recall, instead of using accuracy. In addition to that, training is harder because if you have 10,000 data points of normal operation, one of faulty or fraudulent operation, training something like that is very, very hard because you want to ideally use balanced data sets. So, and that's why there are techniques, there are data set balancing techniques, which will, the simplest ever is if you have a lot of cases of fraud, you have 10,000 cases of fraud and a million cases of normal operation. You can just randomly select 10,000 normal operations and 10,000 frauds, and that's fine. But in some cases, you won't have enough fraudulent anomalous examples to do that. So what do you do in that case? Well, there are generative algorithms that will generate synthetic data that covers essentially these elements will generate artificial fraudulent data points, right? There again, mathematics for that are a bit out of scope for this particular class, as we're keeping it, a bit simpler. But what I want you to know, if you're listening to this, if you ever find yourself on a project, working on a job somewhere, and someone tells you, "Oh, we would like to do this, but we don't have enough anomalous data points," raise your hand. Tell them, "No, there are." We need to get someone who knows what they're doing engineering-wise, because there are techniques that exist that can address this. Please check which techniques exist, which can be implied here. Okay. So we have, so just to, generally provide a conclusion on data mining and some other trends that exist. Essentially, data mining is, as I told you, this is just repeating from before, is we want to take big data, we want to take a lot of data and compress it, essentially extract information in an easy to understand way. As I said, if this then that rules, like if we lower the price, we're going to increase our revenue because sales will increase significantly. Something like that, actionable information that your C-suite executives can use. Or if you're in medicine, something like people who took this medicine versus people who didn't take this medicine have a higher survival rate. That's actionable information that people can take and do something with it, and that's an example, of what you want to do with data mining. Usually, these days you're using deep learning and reinforcement learning in combination with big data platforms to automate that. So HDFS, Spark, and the other techniques that we mentioned, like Kafka, Storm, etc. Challenges exist, especially when it comes to data mining, to actually extracting information, and that's unstructured data, real-time processing, because maybe you want to see what's going on in real time. As I mentioned, it's easier when you want to process that later on. And what will happen in the future? Usually, based on the current trends that we have, it's AI, and more AI. I wrote here like automation, AI integration, improved algorithms, because it sounds stupid to me to just write AI 5 times in a row, especially natural language processing. That's something that's going to get applied more and more and more when it comes to extracting information and forming information. Because now, I'm an engineer. I'm not great at talking and conversing and explaining stuff, especially to management, but I don't need to anymore. I can write a code that will automatically report stuff. I've done stuff like that. I've done projects like that where I've took information that was collected from multiple data sources, fed it into a large language model like ChatGPT, and created essentially a blog post that was then emailed to people. Again, I can go into more details due to NDAs, but that's something that I've already worked on recently. Because why? Because those people who are getting that information want to get it in a nice, readable, understandable way. So I made a platform that basically collected numbers, turned them into graphs and text, and emailed them to people. That's something that's happening more and more today. And again, you have to do that. Data mining is crucial in various industries to basically make sense of the data that was collected, because I'm repeating that data on its own doesn't have a value, right? Okay, so before we finish for today, I'm going to, just building on this, what I just said is I want to introduce something that's called data storytelling. So what is data storytelling? It's basically you take data combination, you want to explain that. What I just said right now, the types of project that I did is where you have information, and if you send someone an email with 20 numbers inside them, they're going to ignore it. If you write them a short paragraph of text and show them a couple of graphs, they're going to pay attention to that. And that is what essentially it's storytelling. Create it create information, take information that you have, take that insight. So it's a step above, this, I don't know where I wrote them, the start for KDD is basically this knowledge representation on a higher level. One step above this, it's a part of this knowledge representation, but it's more than just representing that in a single element, with a single number. It's actually telling a story. Why is that important? Because it helps you keep attention of people. My mentor told me I had a presentation. I did something that was pretty interesting with scientific data. I was at a big conference, and it was one of my first conferences. And they go down and asked me, did I do well? Because I was worried about how I presented. He said, you presented great, your form, but the problem is you did not many people understand what you're doing because you didn't sell them the story. On the next conference you go to, you're going to come up with a story that explains why this is important. And I did that. I explained to them, I told them a story about, hey, imagine this happening. Imagine this problem happening. I was talking about synthetic data, generally determining whether data is synthetic or not. And in the first time I heard the presentation, how people reacted to it, because I was talking, oh, it's important to detect data. This is how we do it. And I lost people. I lost their attention. On the second case, when I presented it, I said, like, imagine that you invest 3 years of your time developing a data model based on the patient data you received from a hospital. And then when you go to publish the paper, you receive an email informing you that the database that you were working on for the last 5 years, that you wrote many papers on, maybe you're basing your PhD on it, maybe something like that. It's not real, it's a synthetically generated data. And now you can't, maybe the product you are trying to validate right now, maybe the paper you're trying to publish, maybe the PhD you have to submit by the end of the month is not valid anymore because you haven't trained it to real data. And that's why detecting synthetic data in advance is important. Let's talk about how we can do it. And everyone was laser focused on me because they wanted to see how they can accomplish something like that. How they can actually check for synthetic data when they're dealing with big data tasks. Because I had that story, I wanted to sell them and keep their attention, right? And that's something that's super, super important. So we want to present the data in a very clear way and give it context. So if we say something like this is going to improve our sales by 1%, maybe that 1% is massive, but 1% is 1%. It's hard to understand what it means in context. If you say something, this is going to improve us by 1%, and 1%, and to put that in context, that's 10 million euros in revenue. 10 million euros is something that people understand much clearer than 1%, right? Again, you want data to be clear. You want to use visualization. You want to show graphs. You want to have a narrative structure where you're going to give, as I said, you're going to give context. You're going to explain in context why is that important. You're going to have that middle where you're going to actually describe how we are coming to this conclusion that we are coming to. And in the end, you're going to give actions. We're going to give conclusions and we're going to give actions, actionable insights. I used that term before because if you just give data, this happened to me also in the past where I worked on something and I just presented data and I wasn't confident, in my capabilities as an engineer, as a data scientist, and I was like, "Oh, here is the data. You figure it out yourself," and no one cared, right? No one wants that. You want them to tell them, "Hey, this means this, or this means if you want to improve your sales based on the data, you need to lower your prices. If you want to increase the survival rate of this operation, you need to use this technique compared to this technique because the data shows it." and you need to sell that as a story. You need to sell that as a personal story of a single patient, because there's that horrible quote that's attributed to a lot of different people that says a death of a person is a tragedy, a death of a million is a statistic, right? And if you walk into selling a story about how we had 400 patients that suffered from this disease, 200 patients were treated in this way, 200 patients were treated in that way, and these people that were treated in this way had a higher survival rate. Right, it's people won't care about what you're talking about. They're going to be on their phone. They're going to shut up. If you tell them something like, I had a friend who was suffering from this disease. He walked into hospital and he was given a choice. And the doctor told him, you can do this or you can do this. And that's what motivated me to run this analysis. I actually wanted to know, and we did this, and then I analyzed it and I showed it. And what it shows is that if you get a situation like that, where my friend has walked in there, and sadly and happily, my friend, because the doctor took this decision, they actually implemented this technique. My friend survived, and we are still, friends. We hang out each day. We are happy. That's something that people understand on a personal level, and will connect with that story and will help you understand. You need to be able to sell your data. If you aren't able to sell your information, if you're just going to show, like us engineers tend to, just going to show 5 different numbers, people won't understand it, right? People won't connect to it, and they won't care about what you did, because I would prefer if everyone was like me, and if you showed them 5 numbers, they would understand it and figure it out and be like, oh, yes, this is 56%, this is 54%, we're going to go with the 56%, it's more optimal. While people aren't like that, and you need to sell them stuff. How you can accomplish this better is, choosing right visuals, showing them in a clear way, a simpler way that helps you understand, what's going on, what's happening, and how to better illustrate the data that's going on there. Simplify data. As I said, if you're talking about a million data points, people are going to get lost. Break it down. Focus on key elements in there. Don't show entire data, or talk about that. It's just focus on discernible parts of the data. Focus on what the goal of the analysis is, what your conclusion is. Take that from the start and move forward with it. Use, contrast, color, visual elements are super important when you're presenting something. Do yourself a favor if you're in a job where you find yourself presenting stuff often. There are a lot of great courses on YouTube that you can look into, and you can understand what to use where, what kind of information you convey when you're making certain decisions, how to make sure. For example, one of the simplest examples, always have 2 versions of a presentation. If you're presenting live, have one with a light background and dark text, and one that's the opposite, because depending on how the lighting is in the room, one or the other might be better visible, and you can easily generate 2 copies of the presentation. And again, make stuff relevant. As I said, you're telling a story of, my friend walked in, they were sick, I was scared. That's something that people have experienced. That's something that people have experience with. If you're talking about smart cities or something like that, talk about getting stuck in traffic. Talk about stuff that people understand. People don't understand numbers. Most people don't deal with a lot of numbers on a daily basis. That's something that, so you want to humanize your analysis, your conclusion. And where you can apply this anywhere, but especially, if if you're a computer programmer talking to other computer programmers, my experience is, if you're try to do something like this, people are going to get annoyed. People are just going to be like, no, show me the code, show me the numbers. If you're talking with data scientists, if you're talking just with scientists in general, people are, people are who are actual scientists are going to get a bit pissy if you try to oversell stuff, right? They're going to be like, why are you telling me about your friend working as somewhere? Just show me the data, right? That's how scientists are. But in general, if you're talking about business people and marketing people, especially marketing people, if you start telling them how the standard deviation demonstrates that using technique A instead of technique B is no, you want to tell them, hey, I showed this to my kid and my kid preferred version B, right? And then I analyzed the data and I figured out that not only did my kid prefer the version B, but most people prefer the version B, right? Because it's nicer, it has a bigger, text, it's more eye-catching, yada yada yada. Sell the story. Those are the people who need to sell the story. Same goes for healthcare. A lot of doctors, if you are here in medicine, I apologize, but in my experience, a lot of people in medicine aren't numbers people because you need to focus on different types of things. So, introducing stuff, for example, for healthcare, you can use more numbers in healthcare than you can in marketing. Because marketing hates numbers unless it's percentages of sales or something like that. In healthcare, you can use some numbers, right? But don't focus on individual data or something like that. Focus on the actual improvements in health and stuff like that. If you're talking about stakeholders are business people. Don't forget that. Don't treat stakeholders like doctors. If you're talking about people who are actually running the hospital as a business. Public policy, politicians, staff, especially politicians are either actually busy or they try to present themselves as busy. If you're showing them anything, not just politicians as in your mayor, but anyone who's involved with politics, make it snappy, make it quick, make it short, make sure everything is presented quickly, because that's how they like it. And that's basically, your goal is to present stuff like that. So that's essentially data storytelling is super, super important. If you actually want your data, your analysis to be utilized somewhere and to be presented, and you need to pay attention to it. I know that if you're an engineer or something like that, you're like, oh, who cares? It's just like data is data, no matter how it's presented. But believe me, there's a big important difference in how you present your data if you want that, actual if you want that actual access, you want actual money, funding coming your way, you want to sell a product, you want something like that. So don't forget that. And if you aren't great at it, I know a lot of startups who hire people specifically for sales, because they need someone for sales. And some of the greatest salespeople that I work with are people who have very little knowledge about engineering. Despite them, I won't name names, but I recently worked with a company on a very large purchase as a consultant, and the person who was selling that, I know him personally from before, and I know he isn't a great engineer. We went to college together, and but once I saw him, and my intention was like, what is this guy doing here? He's going to, present stuff about cylinders and this, that, and I know he's a bad student, but he was a great salesman, right? So if you're ever in a startup or something like that, or in a company, and you can identify that you yourself aren't a great salesman, or that other people that you're with aren't great salesmen, hiring someone for that, for just doing that, it is very beneficial, and it's something that companies actually do, right? Okay, so that I wanted to end with this like a bit lighter topic, just more discussion topic for today. So what do we have here? Well, in the next we have two more, if I'm not mistaken. Let me just check the schedule. Yes, so we have on Monday and on Tuesday, we have 2-hour lectures in big data. We're going to cover certain elements here, so the next time we're going to talk about big data in cloud, as you can see here, and we're talking about performance. We're going to focus a bit further on how to actually improve performance in big data systems. So it's a bit more engineering focused. And on Tuesday, we're going to have just generally talking about addressing data issues, how you can deal with individual data elements, and just focusing on the future of big data, what's going to happen, what the trend is pointing towards, and so on. So that's it for today. We are ending a bit early. My apologies for that, but I have another lecture we have a practical data collection. If you are listening to that, we have it at 1 p.m. So I decided to finish a bit early today so I can have a bit of a break and I'm not teaching for 8 hours straight. So yeah, I apologize for that, but it's how it's going to be. Yeah, if you have any questions, if anything was unclear, you can feel free to email me, right? And that's it. So thank you very much, and see you on Monday. Goodbye. I see someone raise their hand. I don't know if that was on purpose or I assume not. But in short, if you raised your hand, you wanted to ask me something, feel free to email me. I will type my email once again in the chat in case you need it. Other than that, here it is. Other than that, have a nice weekend and see you Monday.
Thank you for the lecture. Have a nice weekend.
Have a nice weekend. Bye.